All right, let's take a look at the maximum modulus principle. Section 54. Okay, so this gives us a property of analytic functions that's valid in the complex setting and not in the real setting, another one of those. We'll have a handful of statements of the maximum modulus principle. We'll start with lemma 54.a, and I mean, arguably some folks might even take that as the maximum modulus principle. But let's look into that, see what it says, and start to decipher why this thing's called a maximum modulus principle. So the setting in the lemma is, suppose the modulus of f of z is less than or equal to the modulus of f of z0 at each point z in some neighborhood, mod z minus z sub 0 less than epsilon, in which f is analytic. Okay, so the hypotheses are analytic function. It's analytic in a disk centered at z sub 0 with radius epsilon for some epsilon greater than 0. So we got a little open disk about z sub 0 on which the function's analytic. And this part here with the moduli means that if we look at the modulus of f of z throughout that neighborhood, the maximum of the modulus occurs at z sub 0. Possibly occurs other places as well, but the modulus throughout this neighborhood, as z ranges over that neighborhood, the modulus doesn't get any bigger than the modulus is at the, just so happens it's the center of that disk, the point z sub 0. Okay, so that's the reason it's called a maximum modulus principle. It sounds kind of humble. You get no behavior like this from a function of a real variable. I guess we'd interpret maybe the modulus is absolute value in the real setting, and it ain't hard to come up with a function that on, say, an open interval has its maxima occur internal to that. I need to read the conclusion before we get too carried away. Conclusion is, then f of z is a constant function. It takes on the constant value f of z sub 0 throughout that neighborhood. But if you'll think of maybe a function negative x squared or 1 minus x squared, a nice continuous function, be a concave down parabola, and we take an interval that includes the vertex, the x coordinate of the vertex, then it's got its maximum inside that interval. Maybe 1 minus x squared on the interval negative 1 to 1 is a good example. Nothing like this holds in the real setting. So if the maximum of the modulus occurs at this point z sub 0, then the function is a constant function. Okay, that ain't my favorite statement of the maximum modulus principle. We'll use this to prove another version. It also isn't my favorite, but we'll have, I think, at least 3 versions. I like one of them better than the others. This reminds you possibly a little bit of Louisville's theorem. I mean, the conclusion there was something about then the function is a constant. Here, it seems like more humble hypotheses. This is a little local behavior on this little disk centered at z sub 0. Louisville's theorem required a good deal more in terms of behavior at various z values. Okay, so let's look at a proof of that. Okay, so we're in section 54. Whoops. Okay, and there we go. All right. Suppose we have those hypotheses that the modulus has a maximum in this setting at the point z sub 0. All right, so this has to be a discussion that's held very locally. It's in that little epsilon neighborhood of z sub 0. So we're going to choose some other point, z sub 1, other than z sub 0, in that epsilon neighborhood. All right, let rho be the distance from z sub 1 to z sub 0. And then we're going to take a little circle, c sub rho, a circle centered at z sub 0 with radius rho. So what we've got is a little circle concentric with a circle, the boundary of the neighborhood, and with a smaller radius because we chose z1 to be in the epsilon neighborhood. So we've got z sub 0, we've got an epsilon neighborhood, and then inside that, we've got this little c sub rho thing that we've defined. In particular, z sub 1 lies on c sub rho. All right, so what we have for function f, it was analytic in this open neighborhood. This little c sub rho deal then is a contour that's purely inside that neighborhood. And so f is analytic on and inside c sub rho. And under those conditions, Cauchy's integral formula's got something to say. It's got this to say. F of z sub 0 is 1 over 2 pi I, the integral around c sub rho, f of z dz over z minus z sub 0, Cauchy's integral formula. All right, it involves the f of z sub 0. We want to have a conversation about the modulus of that, so it's coming. All right. So take that c sub rho, parameterize it as z equals z sub 0 plus rho e to the I theta. All right, so we're going around this little c sub rho circle. It's a circle centered at z sub 0 with radius rho. So as theta varies, we travel around the c sub rho circle, mod z minus z sub 0 equals rho. Then we can rewrite this integral using this representation. So we'll replace z with z sub 0 plus rho e to the I theta here and here, producing this and this. Oh yeah, we'll need the dz part. So calculate a corresponding differential or take the definition of contour integral. And we get the derivative of this with respect to theta times d theta. So differentiate with respect to theta, z0 is a constant, rho is a constant. So we'll get rho I e to the I theta. So the chain rule will introduce another I. So we get I rho e to the I theta d theta. That's the z prime of theta part, the dz part if you like. And then let's simplify that. All right, so we've rewritten this integral in this form. Get some z0 minus z sub 0 stuff going on in the denominator. So those will cancel out. Got a rho here and here that'll cancel. Ooh, an e to the I theta here and here that'll cancel. That just leaves us with an I, but there's an I out front. So those will cancel as well, leaving us with a 1 over 2 pi integral 0 to 2 pi f of z sub 0 plus rho e to the I theta d theta. We know that equals f of z sub 0. We're going to call a little attention to this after we finish the proof here. We're going to call this Gauss's mean value theorem, I think it is. This little equation, f of z sub 0 equals 1 over 2 pi, which by the way is the length, well, 1 over 2 pi. Sorry, 2 pi rho is the length of that contour. We're integrating, there we go. It's the length of the interval of the theta values. But we'll make a comparison with the average value theorem from Calculus 1, since we can. But continuing on with the proof of the maximum modulus theorem. All right. Let's take moduli. Right. There's something in the hypotheses involving the modulus of f of z sub 0, so we need some of that going on. So we'll take a modulus of f of z sub 0. We'll take a modulus of this integral. If we move those moduli signs inside the integral, I guess it was lemma 43.8, tells you that introduces an inequality. So we get mod f of z sub 0 is less than or equal to, real number, integral 0 to 2 pi, modulus of the integrand. So lemma 43.8 told us the integral is less than or equal to the integral of the modulus in this d theta type setting. All right, so we've got mod f of z sub 0 is less than or equal to this quantity. We're going to reverse that inequality on the next slide. But remember, equation 3 left us with f of z sub 0 modulus less than or equal to value of the integral. Okay, now we had hypothesized that mod f of z sub 0 was an upper bound for the value of the function throughout that neighborhood. These z sub 0 plus rho e to the I thetas, they're all in that neighborhood. So the modulus of f of those values is less than or equal to the modulus of f of z sub 0 because it's the maximum modulus on that neighborhood. This holding really for any input that's in that neighborhood, we've expressed it in terms of this, basically in terms of the parameter theta. So we get that inequality to hold. Now, if we'll integrate 0 to 2 pi, this left-hand quantity, that's less than or equal to the integral from 0 to 2 pi of the larger right-hand quantity. That's just sometimes called monotonicity of the integral, and this is all just Lebesgue stuff once they put the moduli on it. It's just Riemann integration. It's all just calculus with the moduli. Everything's real, in other words. And let's see, if we integrate 0 to 2 pi f of z sub 0, that's a constant. So we'll just get the constant value times the length of the interval. There's that 2 pi referred to in terms of lengths of intervals before. And now let's divide both sides by 2 pi, and we get mod f of z sub 0 is greater than or equal to the integral. Mod f of z sub 0, take the 2 pi to the other side, we get the 1 over 2 pi, that inequality reverses directions, written in the opposite direction. Integral 0 to 2 pi f of whatever, modulus of d theta. That's what we had on the previous page, only the inequality points in the opposite direction. So the previous slide, equation 3, this equation 5, tells us we've got this equality here. And it's actually that we'll refer to this the equality as Gauss's mean value theorem after the proof. Okay, so this next part's a wee bit tricky. What we're going to do is say, hey, that f of z sub 0, I can interpret that as a certain kind of integral. We've shown f of z sub 0 equals, let's take the 2 pi to this other side. We'll have this integral divided by 2 pi. This integral divided by 2 pi will equal f of z sub 0. All right, we've also got f of z sub 0 equal to this other integral. But we could take the f of z sub 0, if you like, we could cross multiply by 2 pi in this. So maybe that's easier to follow. Cross multiply by the 2 pi, we'll get a 2 pi f of z sub 0 modulus of. So that's exactly this thing here. So we could write this in terms of an integral. Take those integrals, collect them together on the same side of the equation. The arithmetic is accurate here. And then we get an integral from 0 to 2 pi, modulus of f of z minus modulus of f of the z values that are on that c sub rho contour. D theta equals 0. All right, so you should be happy with linearity of the integral. Take the integral over here. On the second part, that would produce this without a 2 pi. Integrating this constant simply produces 2 pi times that f of z sub 0 modulus of. We've got a 2 pi here, a 1 over 2 pi there, and the book's balance. So we get this kind of integral. All right, the following could use a reference for this, but let me try to talk you through it as plausible. It's definitely true. You need a little bit of knowledge about analysis and integrals of continuous functions. Analysis, you need a little bit of knowledge about integrals of continuous functions in the Riemann setting, so calculus 1. All right, we've got an integrand here. Everything's real because of the moduli. This integrand in the parentheses, it's non-negative because remember we assumed mod f of z sub 0 is greater than or equal to all those other function values. So the stuff in parentheses is non-negative. Also, we started with an analytic function. Analytic functions are continuous. Their moduli form continuous functions. And what we've got then is a continuous integrand as well. So the integrand is non-negative and continuous throughout theta between 0 and 2 pi. And we know the integral equals 0. How can you integrate a non-negative function and get out 0? when it's continuous, only when the integrand is 0. So if you think of continuous function, non-negative, if I were to allow it to be positive on some little subinterval, allow this integrand to be positive, not 0, we'd have a little bitty area, a little bit of area underneath that non-negative function, and that violates the fact that the integral of the non-negative function is 0. Yeah, we could use a more authoritative reference than that, but that's the idea behind it. So we can draw the conclusion that the integrand must be 0. That is, modulus of f of z sub 0 equals the modulus of f of z sub 0 plus rho e to the I theta. And this holds throughout theta ranging from 0 to 2 pi. So we've got, as theta ranges from 0 to 2 pi, we've got these input values on that contour c sub rho, circle centered at z sub 0 with radius rho. Okay. So another way of writing this is mod f of z sub 0 equals a modulus of f of z, where we're letting z range over that c sub rho circle. Remember, we chose a z sub 1 back up top. We started with a z sub 0. We chose an arbitrary z sub 1. Z sub 1 was on this circle. We brought the circle up so we could use Cauchy's integral formula. But getting back to that z sub 1, we've got modulus of f of z sub 0 equals a modulus of f of z sub 1. Now, z sub 1 was a totally arbitrary point in that epsilon neighborhood, other than it wasn't z sub 0 itself. Of course, f of z sub 0 equals f of z sub 0. But we've chosen an arbitrary point other than z sub 0 in that neighborhood and shown that the moduli are equal. So we can draw the conclusion that the moduli are equal at z sub 0 and at z, f of z sub 0 modulus of, for any z in that epsilon neighborhood. Now, it's been a while, but back in section 25, chapter 2, we had a result that said, if you have a function that has a constant modulus, then that function must be a constant function. It comes out of the Cauchy-Riemann equations. But for the record, it was an example, and there's your theorem, 2.25.b. So the only way an analytic function f of z can have a modulus that's a constant is if that function is a constant, and that function takes on the value f of z sub 0 at z sub 0, must take on the value f of z sub 0 throughout that neighborhood, and that was the claim. We've got a constant function. Okay? So, returning to the notes, I want something a little more geometric than that, really. Returning to the notes, we'll use this to prove an alternate statement of the maximum modulus theorem. And I called attention to that equality we had. The f of z sub 0 is 1 over 2 pi I, integral from 0 to pi, blah, blah, blah deal here. Remembering the hypotheses where f is analytic on and inside contour, the contour we're talking about here was c sub rho, was the symbols we used in the proof. But we get this equality only under assumptions of analytic on and inside the circle. So this reminds me for all the world of average, the average value of a function from calculus 1. So I say, let's elevate this to the status of a theorem. It's called Gauss's mean value theorem. And we're lacking a lot of results from calculus. We never had a mean value theorem for derivatives in here. Here's a mean value theorem for integrals. If you'll recall in calculus, we define the average value of a function on an interval. Average value of a function on an interval. I'm trying to highlight here. Average value was defined as 1 over the length of the integral times the integral from a to b of f of x dx. That's the average value of function f on the interval from a to b in calculus 1. And if we had a continuous function, somewhere back there you said, this continuous function must assume on the interval a, b, somewhere, its average value. So we're getting a similar type behavior here. This analytic function f, if we were to define this stuff here as its average value, this analytic function attains that average value somewhere. Somewhere in particular, it's right at the center of the circle that we've integrated over in calculating that mean, it turns out. So there's something that's a little parallel to the behavior of the real setting. But back to versions of the maximum modulus theorem or maximum modulus principle. Next version says, if a function f is analytic and not constant in a given domain D, then the modulus of f of z has no maximum value in D. That is, there is no point z sub 0 in D where modulus of f of z sub 0 is greater than or equal to modulus of f of z for all the other points z in that domain. All right, so assuming analytic and not constant, domain is an open connected set. And drawing a conclusion that there is no maximum modulus, no maximum value of modulus of f of z. Maybe one passing comment, of course I can't talk about greater and lesser unless we're talking real numbers, and we are when we take the modulus here. There is no greater than or less than on the complex numbers. Well, we're okay because we're taking moduli and talking modulus of function values. All right, so yeah, fine. I'm not too gung-ho about calling this the maximum modulus theorem when the conclusion is has no maximum. So that's a little odd. But anyhow, this is what Brown and Churchill are calling the maximum modulus theorem. I rather like what we'll state after this, though. But let's go through and prove. Analytic and not constant implies there is no maximum modulus. Back to the notes, to supplements. Okay, so let's go through proof of that. This is proof by contradiction. It's a couple of slides long. It says, let f be analytic and non-constant on D. Assume the modulus does have a maximum value on D, say at point z sub 0. So we've assumed the hypotheses and assumed in direct contradiction to them the negation of the conclusion. So we'll get a contradiction, and by contradiction the assumption will be false, and we will not have a maximum value on D of this function. Okay. Let P be any point in the domain D. Now, I'm going to start talking polygonal lines again. Remember, it's a sequence of lines joined end to end. That's what a polygonal line is. It's polygons, you join in line segments end to end and you go back where you started. We're not requiring that. So it's not a polygon, but it's a polygonal line. That's just the names. So let L be a polygonal line lying in this domain, open connected set, and joining z sub 0 to point P. How do you know such a thing exists? It's a rather involved topological property. In the graduate complex analysis class, we would actually prove that fairly early on. They do a lot of topology at the beginning in that class. Here's a link to the notes on that, but let's take it as given. If you think open set, it should be fairly plausible, drawing pictures in your head. We're going to pick a little distance here. I'm going to break it into two cases. If D is not the entire complex plane, capital D, the domain, then we're going to choose a lowercase d, a number, to be the shortest distance from the points on L to the boundary of that domain. How do you know one of those exists? How do you know there is a shortest? There ain't always these obvious sounding things. Pick the smallest positive real number. Well, there ain't a smallest positive real number. 0 is not positive. It's too busy being 0. It ain't negative either. But you give me a candidate smallest positive real number, I just cut it in half and I got a smaller positive real number. So how do you know there is a shortest distance? Well, see the graduate notes on that. So there's a couple of little topological holes in the argument here, but hey, there's how you plug them. So we're taking D to be either the shortest distance from the points on L to the boundary of D in the event that domain D isn't the entire complex plane. If it is, then let D equal 1. So we've chosen this distance 1. It's a little finite distance is all we need. Okay, might have to bounce back and forth to the picture and see what we're up to here. All right, since L, the polygonal line, is of finite length, there are complex numbers, L equals z sub 0, z sub 1 through z sub n, such that the modulus of z sub k minus z sub k minus 1 is less than d, and for all those k values. And what we're going to do is define a neighborhood of each of the z sub k's such that we're taking all z values within distance d, all z values within distance z of point z sub k. So that's neighborhood n sub k. So we picked a distance. We're connecting together two sets with a polygonal line. Polygonal lines, by definition, are finite in length. That's where the finiteness claim, finite length thing comes in. And we picked complex numbers, z1, z0, z1 through z sub n. And then we put little neighborhoods around them. Little neighborhoods that are not too big. They're less than d, where we've picked this parameter d above. All right, let's go through this last sentence and we'll look at the picture. They say then, the n sub k are all subsets of domain D. That's where the little lowercase d comes in. They're sufficiently small to lie inside domain D. That's what the deal with the distance to the boundary was about. And the center of the n sub k lies in n sub k minus 1. All right, so the center of the next neighborhood lies in the previous neighborhood. So here's what all that stuff means. So we've got some open region. That open region doesn't trim off this n sub 0. We've chosen an open region in such a way that when we choose this distance d that they're talking about, this will keep neighborhood n sub 0 about complex number z sub 0 within that open connected set. Can be done. And then they've chosen the z sub 0, z1, z2, and so forth. They did a little bit better job with the polygonal line in this picture. Over to z sub n with the following properties. We've got these consecutive z values within d of each other. So when I look at the center of the second disk, so we've taken z sub 0 and a disk about it. We moved over to z sub 1. Got a second point, a z sub 1 point, and an n sub 1 neighborhood of it, which lies inside domain D. And notice z sub 1, the center of neighborhood n sub 1, lies inside of n sub 0. We're going to make the radius of n sub 1 d, get this z sub 2 in there, on this line, and so forth. So they've done this in such a way that these consecutive z values lie along this polygonal line, and they're like close together. They're within d of each other. And these are little open neighborhoods. And we were just talking about little open neighborhoods in that lemma. All right. Modulus of f of z sub 0, we supposed, was a maximum of the modulus of f of z throughout this domain D everywhere. So it's a maximum on n sub 0. All right. So we've got a maximum, a maximum of the modulus of f of z at z sub 0. And we've got a function that's analytic in this little open neighborhood. In the notation of the lemma, we'd take the radius, took it to be epsilon, not rho, it was epsilon in the lemma. Here we're taking it to be this parameter d. Well, we're good to go though. Lemma 54.8 does apply to say, hey, the only way you can have a maximum on this little open neighborhood, and we're saying we got a maximum everywhere, but not the conversation yet. The only way you can have a maximum on this open neighborhood n sub 0 is if that function is constant on this neighborhood. And in particular, whatever value it takes on at z sub 0 takes on the same value at z sub 1. F of z sub 0 and f of z sub 1 are the same. Now let's move over to the second neighborhood. All right, same story, except now we've got a maximum of f of z sub 0, modulus f of z sub 0, on this second neighborhood, but that's the same as the modulus of f of z sub 1. Dude, you got an open neighborhood, a disk, function analytic inside that disk, maximum occurs here, got to be constant. Takes on the same value at z sub 2. And so the plan is to inductively walk across these neighborhoods and at each stage show constant function, constant function, constant function, constant, 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 constant function. So whatever value it has at z sub 0, got the same value over here at z sub n at point P. The reason we did it this way is the lemma applied only to little disks, so we had to come up with a setting where we could discuss a bunch of little disks. But we've got f of z sub 0 taking on the same value, f taking on the same value at z sub 0 as f takes on at point P. Point P was an arbitrary point, f of z sub 0 equals f of P, then f could only be constant on that domain D. But that's a contradiction. And if I look back at the statement, let's do that. So we've got a non-constant function. Analytic not constant in domain D. We made an assumption. That assumption's false because we violated the hypotheses of constant function. The assumption that mod f of z has a maximum in D must be false, and so mod f of z must have no maximum in D. So there's a maximum modulus theorem for you. As stated, it says there is no maximum modulus. Okay, that's because they're using open connected sets. They're using domains here. We can tweak that a little bit, and I prefer this version. I forget if this is in the book or not, but I prefer this version of the maximum modulus theorem. All right, and this time we're not dealing with an open neighborhood. In the lemma up there, we had an open neighborhood, the epsilon neighborhood of z sub 0. Here, we've got a domain. Domains are open connected sets, so there's still that openness. We're going to change things. Down here, we're going to talk about closed bounded regions. For the record, a region was an open connected set. We even have to have connected. It included some part or all of its boundary points. Here we're good. We got a closed and bounded region. You'll call those compact sets in senior level analysis. And we are seeing a maximum of the modulus, and it occurs in a particular place. Hypotheses are a little bit more stringent in this one. Suppose that function f is continuous on a closed and bounded region R, and that it's analytic and not constant in the interior of R. It's the first time we've seen that. It's analytic inside and only continuous when we try to extend from inside to the boundary. So we didn't get any assumption about analytic on the boundary. Like we've had analytic on contours a lot when we were doing integrals. But we've got analytic interior, let's see, closing boundary region, that is analytic on the interior of R. Also, it's not a constant function. Okay. The claim is then the maximum value of mod f of z on R, which is always reached, which always exists. There's a reference for you on that. It's continuous function on a compact set, maxima occur. But maxima only makes sense when I move to the real setting. We did because we took moduli. And occurs somewhere on the boundary of R. All right, so this is a lot cleaner. It says maximum value of the modulus, the maximum modulus of the function, exists, and there's where it occurs. It occurs on the boundary of the region, and never on the interior of the region. All right. What we had in the previous statement, on which this will be proved, says analytic not constant on an open region. Well, in that case, mod f of z had no maximum. All right, well, if we just looked at the interior of this region, we'd be in the same setting. So what happens is this has no maximum on the interior, but it's got a maximum. I guess theorem 2.18.3 tells you that, continuous function, compact set, has a maximum. Real value I need in there somewhere. So we know the maximum exists and we know it ain't on the interior. So guess where it's gotta be? It must be on the boundary because that's the only place left. And that's how the proof of that goes. So this one's a little more tame. Okay, actually there's the proof, one slide. Let capital M be the maximum of mod f of z on this region R, so that mod f of z is less than or equal to capital M throughout the region. If f's constant, then we'd get mod f of z to equal M for all z, and the maximum would be attained on the boundary. So if it were constant, we'd still have the maximum attained on the boundary. If it's not constant, more interesting, then by the maximum modulus theorem, as these guys have stated it, the maximum of the modulus can't be attained at an interior point. Well, you know it has a maximum. It's attained somewhere. Theorem 18.3, 2.18.3 again. Oh, well, if it ain't on the interior, it's got to be on the boundary of region R. Problem solved. For the record, a region is an open connected set along with some, none, or all of its boundary points. It's been a while since we talked regions, probably. Okay, so the maximum does exist and have to be on the boundary. So I prefer that as a statement of the maximum modulus theorem because it talks about the existence of a maximum modulus versus the non-existence of a maximum modulus. We've got one additional little result concerning really harmonic functions. Let f be continuous on a closed and bounded region R, analytic and not constant on the interior of R, for f of z equals u of xy plus iv of xy. We do the usual x plus iy thing for z. The function u of xy attains its maximum value in that region on the boundary of R and not on the interior. Okay, let's look at that. So the proof is quite easy with what we know. It says almost the same thing as what we've got upstairs, but Jesus talks about a real valued function of two variables. It's the real part of that function f. Whereas up here, we talk about an analytic function. So down here, we're talking about the behavior of the real part. Now, when we say region, technically, we'd have to have a region in the Cartesian plane, in the xy plane, whereas up here, the region was in the complex plane, and these are different mathematical structures. Of course, they're intimately related. Let's look at the proof of that. It's a quick one. All right, and there's that one. And what we're going to do is exponentiate, and then that imaginary part will vanish. So define g of z to be e to the f of z. Then g is continuous on R, composition of continuous functions. It's analytic on the interior of R. Chain rule tells you that. We knew f was analytic. The exponential function's analytic everywhere. There's some theorems to justify it. And let's take the modulus of g of z. Well, the modulus of g of z, that is the modulus of e to the f of z. F of z we have written as u of xy plus iv of xy. Properties of exponents allow us to write this as a product. Property of moduli allow us to break it into a product of moduli. And hey, the e to the I whatever, that has modulus 1. So we can lose that, and we're just left with a modulus of e to the u of xy, and we're in a real setting. But exponential functions in the real setting are non-negative, so we can even drop the absolute values. These would be, because I could interpret this one as absolute value and this one as modulus. This is real, this is complex. So we get for the modulus of g of z, we get e to the u of xy. All right, we just saw that g of z being continuous and analytic in the appropriate places, that's going to attain its maximum on the boundary of the region and never on the interior. Okay, well, the exponential function, e to the whatever, that's an increasing function of real variable x. So we get the biggest value out of the modulus of g of z when the exponential has its largest input. So u of xy attains its maximum at the same point on the boundary of R. Maxima of g of z correspond to maxima of u of xy, and minima correspond to. Attains its maximum on the boundary of R. S not constant, so the maximum can't occur on the interior because of the properties of the g function, again, by that corollary we just saw. So this I'm a little less interested in because it's a result about a function of two real variables. Yeah, they're peripherally interesting. The interesting result is definitely the maximum modulus theorem, alternative version, I say. There's an exercise somewhere in the book called the minimum modulus theorem. The proof of it is quite straightforward. We're about to make some hypotheses, and the proof of the minimum modulus theorem will be apply the maximum modulus theorem to 1 over f of z for the function you're about to be given. Ooh, 1 over f of z, I'd be worried about some division by 0 there. So let's see what we got with the minimum modulus theorem. That f be a continuous function on a closed region R, let it be analytic and not constant throughout the interior of R. That's how the last couple of results started. Assuming that f of z is non-zero in that region, that's new. Then the modulus of f of z has a minimum value in the region, and that minimum of value is attained at a boundary point and never at an interior point. All right, so it deals with modulus, it deals with the minimum value of the modulus, it deals with it actually happening, it attains this minimum, and it happens on the boundary. So both maxes and mins for analytic functions on appropriate regions are attained on the boundaries. With little added hypothesis here that f of z is non-zero. Well, you can't get any less than 0 in modulus. So of course 0 would be a minimum. And the way the proof of this works is you're going to consider the reciprocal of f of z and apply the maximum modulus theorem. Well, if you take reciprocals, 1 over big things or little things, so maxes become mins and mins become maxes, and you got a problem of division by 0 if we didn't add this hypothesis. So this pops in here for maybe some intuitive reasons. Well, I certainly can't get a modulus less than 0. Moduli are non-negative. And the proof is based on taking the reciprocal of this f function and applying the alternative form or whatever, alternative version of the maximum modulus theorem to 1 over f of z. This hypothesis will guarantee you 1 over f of z is nice and analytic where it needs to be. There's also, actually there are a number of different versions of the maximum modulus theorem out there, maximum principle, some call it. Here's a link to my graduate complex analysis notes with several other versions of the maximum modulus theorem. Let's just read this one last one. This is the maximum modulus theorem for unbounded domains, of which there's several versions of this as well. I call this simplified version 1. To match up with my graduate complex analysis notes. It says let R be greater than 0 and suppose f is analytic in mod z greater than R. Okay, so we're looking at an unbounded domain, unbounded open connected set. We're looking at a circle, mod z equals R, the exterior of that. So we're looking at the exterior of a closed disk. So it's the open exterior of that disk. Supposition of f is analytic outside that open disk. So that's, everything except in here. So that's a bunch of complex numbers out there. So that's quite a hypothesis. Analytic except inside this little disk of radius r. Continuous on the boundary of that region, the circle of radius lowercase r. And bounded by capital M on that boundary. So you might expect, hey, if it's analytic in that unbounded domain, then I'd expect the maximum to occur on the boundary. You need a little bit additional behavior. We need the limit as the modulus of z approaches infinity of the modulus of f of z to be less than or equal to m. And then the claim is this m really is a bound that's valid throughout the region mod z greater than or equal to r. Throw it in that boundary. And that maximum occurs on the boundary. I'm going to choose my words carefully here. You're thinking in this setting of the boundary consisting of that circle, the little circle of radius r, and also, forgive me, the point at infinity. So you've got m as a bound on the circle of radius r, and also, let me use a good caveat here, in some sense, you've got m as a bound at infinity. There is no at infinity. In this sense, that's the some sense, damn it. And whenever I say infinity, there's some limit stuff involved. So we've got the function bounded on the boundary circle and, bounded way out there by capital M. Then it's bounded throughout that giant region, by that same value M. And that maximum occurs on the boundary. It occurs on the circle mod z equals r. And there's several variants of that, and the hypotheses can be weakened a little bit additionally. But there's a good healthy dose of the maximum modulus theorem. What we'll look at in the next section is some applications of it to some results involving polynomials. I'll see you there. Have a nice day.